Hello and welcome to this lecture. In the previous lecture, we saw introduction to Bayesian estimation, how you think of the parameter estimation problem in a Bayesian setting, assume the parameter to be a random variable, then think of this two-step choice. First, choose a parameter at random and then pick the samples according to that parameter, observe the samples, ask the question of what's the probability that the parameter was something given the samples is something else. You use Bayes rule to unravel that. Okay, so let's see a few examples. There's lots of interesting simple examples, slightly more complicated examples. So we'll see all these examples in this lecture. Okay. So first question is how to pick prior. There are generally 2-3 classes of priors that people will talk about. One is what's called a flat or an uninformative prior. Okay, so you just pick the prior to be flat. It's uniform over the range. So now you remember posterior is proportional to likelihood times prior. If prior is flat, then posterior is sort of roughly like likelihood. So you can expect something similar to maximum likelihood maybe, right? So something similar there, okay. Something else which is interesting is conjugate prior. Okay, conjugate prior is one of the most interesting classes of prior distributions out there. In many cases, people like to use conjugate priors. So in this case, you want the prior and the posterior to be from the same class of distributions. You remember we saw so many class of distributions, right? Gamma distribution, Poisson, normal, beta. We've seen so many classes of distributions. Is there a prior which when multiplied by likelihood will not change its class? Okay, so let's say prior is normal, you multiplied by the likelihood of the samples, but you still got a normal distribution as posterior. Okay, same thing with beta. I mean, if you pick prior as beta, you multiply by the likelihood, you still get another beta distribution. Are there situations like that? And that situations, conjugate priors are very, very popular. So, I mean, it's sort of there's a symmetry, invariance in something, and usually when you see invariance, there's something interesting in nature, right? I mean, total energy is invariant, total momentum is invariant. These are interesting natural laws. So you think that when you see a conjugate prior where, you know, the prior is such that after observing the data, the posterior does not change, there is something invariant and maybe there is something interesting. So this is always, it's just a high level justification for why conjugate priors are interesting. The last part is informative priors, where you have some expert opinion or scientific models for justifying that. There's in fact one more type of priors where people pick improper priors. Priors are not even probability distributions. So that's also something interesting. We won't look at that in this case. Okay, at least in this course we won't look at such things. Okay, so I've said something about priors. Let's see examples. Okay, so first example I'm going to show you is Bernoulli samples with a uniform prior. So we saw Bernoulli samples with a discrete prior. Okay, it seemed discrete is difficult to motivate. Why should it be only 0.25, 0.75? It doesn't make sense, right? What is more interesting as a prior is you have x1 to xn being IID, Bernoulli. You know, I'm using the bold face here. So you see here I'm using bold face. Why is that? Just to indicate that this bold face is a random variable. It's not a constant. Just to emphasize that this p is a random variable, I'm using bold face here, okay. So how is this p chosen? It's chosen uniformly from 0 to 1. It's a continuous distribution. You remember the continuous distribution uniform, it'll have a PDF which is flat, right. So this is the PDF of the uniform distribution. It's flat between 0 and 1, any range, any value between 0 and 1, sort of equally likely, any interval. The same width is equally likely. Okay, so that's the prior distribution. So what is the setting here? I'm picking a p uniformly at random from 0 to 1, and then I'm picking n samples from the Bernoulli distribution according to that chosen value p. Okay, that's my Bayesian setting. Then having observed the samples, what's the probability that p took a particular value, right? That's the Bayes rule. Okay, supposing you observed samples small x1 to small xn. Okay. The posterior asks the conditional distribution of p given that I observed these samples, x1 equals x1, xn equals xn. Okay, so this is a conditional distribution. So we know that the posterior density, so remember this will be again continuous, so it will have a density. Okay, so this p given this will be a density. That density is going to be proportional to, this is the prior density. Okay, we know this way in which Bayes rule sort of applies in the continuous world, right? You have a discrete and a continuous thing mixing. So, you condition on the conditional, the continuous random variable taking a particular value small p times the prior density, and what do you multiply by? The probability that x1 equals small x1 so on, given that the this boldface p equals small p. Okay. So, you chose a particular p, and what is the likelihood of observing this, and this is prior. Okay. So, hopefully this is clear to you. This is a mix of continuous and discrete random variables. Again, posterior is proportional to likelihood times prior. In this case, because of the continuous thing, you have densities here. The prior is a density, posterior is a density, this is the likelihood. Is that okay? So, now we can simplify. So, this one is just 1, right? This is equal to 1 for 0 less than p less than or equal to 1. So, that is the prior density I showed you. This is uniform. Okay, the uniform is prior. So, it is just 1. What about this guy? Given that the probability of a Bernoulli distribution, the Bernoulli p is actually a small value p, what is the probability that you observe x1 through xn? That is just p power w times 1 minus p power n minus w, where w is what? The number of ones in the samples, right? How many ones you saw in the samples? You raise the small p to that power. How many zeros you saw in the sample? It's n minus w. You raise 1 minus p to that power. So, that is the probability. And the prior is just 1, it just multiplied, it did not do anything. So, the posterior density is something that is proportional to p power w 1 minus p power n minus w for p between 0 and 1. Okay. So, this density we have seen before. You can go back and look at the densities that we saw before. A density, so notice this is a density, right? The PDF is proportional to p power alpha, let me not say alpha, w 1 minus p power n minus w for the range 0 less than p less than 1. So, this is the PDF which is the posterior density, okay, and w is some value, w could be 0, 1, 2, so on, right. So, some value here, and the PDF is proportional to this. This is a known distribution, this distribution is a beta distribution. Notice what has happened here, it is an important thing to notice. The prior distribution was uniform between 0 and 1, the likelihood multiplied the prior and made the posterior distribution into a beta distribution. Okay. So, that is what happened here. So, notice how the posterior is changing, it is influenced very nicely by the prior distribution and by the likelihood. Okay. So, the posterior density, so if you remember the beta parameter, right, what is the beta density? Beta of alpha comma beta, okay, is actually PDF is proportional to x power alpha minus 1, 1 minus x power beta minus 1 for x between 0 and 1. So, this is the beta density, okay. All right. So, you can look up one previous lecture where we did beta density, this is the beta density. So, here we have p power w 1 minus p power n minus w. So, the posterior density is actually a beta, or posterior distribution is actually a beta distribution with parameter alpha being w plus 1. Okay, why? Because here you should get alpha minus 1, right. So, this is w plus 1. So, p power alpha minus 1. So, you got w here. Likewise, the beta became n minus w plus 1. Okay. Now, the mean of this distribution or expected value of a beta distribution is alpha by alpha plus beta. Okay. So, this is also an important thing, and that is what is used here. The posterior mean is alpha by alpha plus beta, and that is alpha. Is that okay? So, it is just a plug-in to get the answer. Okay. So, a lot of results were used here, a lot of busy things happening. Look at it, take your time, stare at this for a while, you see how we are able to quickly derive the posterior mean and get an estimator. Look at this estimator, right. So, now posterior mean, I know I am going to estimate p hat like this, right. P hat is posterior mean, it is a very popular way to estimate this. It is x1 plus x2 plus xn, w is what? W is just x1 plus xn, right, sum of all the samples. But there is this plus 1 and n plus 2. This plus 1 and plus 2 is there, that comes from the prior, right, that comes from the prior. So that is what you get. Okay. So, we can convert this posterior mean into a estimator, and you replace the small x's with the capital X's, right. That's the standard way in which we go to the estimator. So this p hat is x1 plus xn plus 1 divided by n plus 2. So some of you may remember the ML estimator, right. So what is p hat ML? It's actually x1 plus xn by n. Okay, so this is the estimator for the sample mean, isn't it? So notice how close these two are. Okay, how we started with some prior used beta distribution, this, that, all sorts of complicated things, but we got something very similar to the ML estimator that we had before. Okay, interesting, right? So the uniform distribution, like I mentioned, if you put a flat prior, what you get from the Bayesian setting will be very similar to the maximum likelihood setting in some sense. Okay, so I'm going to make a few more observations. Okay, so before that, we'll change the prior. Okay, so previously we had uniform 0, 1. I'm going to change the prior. I'll make the prior itself as beta alpha comma beta. Okay, so the prior is now not 1, it is proportional to p power alpha minus 1, 1 minus p power beta minus 1. The reason why this is interesting is the posterior is also a beta distribution. If the prior is a beta distribution, the posterior is also a beta distribution. It's very easy to see, right? The previous case, we saw how the likelihood was just 1 p power w, 1 minus p power n minus w, and the prior was just 1. Now in this case, the prior is not 1, it is p power alpha minus 1, 1 minus p power. So there's only p and 1 minus p, they will start adding. So you will get p power w plus alpha minus 1, 1 minus p power n minus w plus beta minus 1. Okay. So the posterior is now a beta density, and that beta has parameter w plus alpha and n minus w plus beta. So one of the things to remember is, if this beta, a special case of beta is also uniform. So we'll come to that a little bit later, but let me continue this, finish it off. So the posterior mean is w plus alpha. So in general, if you were to use a beta distribution as the prior for the Bernoulli P samples, you will get an estimate of this form. A few observations about the prior. Beta, like I said, is alpha beta is non-negative, and then PDF is proportional to p power alpha minus 1, 1 minus p power beta minus 1. An important question, how to pick alpha beta? Supposing you want to use the beta distribution in a Bernoulli sample setting. Okay, how do you pick alpha beta? Okay, I'm not going to answer that question now immediately. In the problem section, when I solve problems, I will show you one method to pick alpha beta. Okay, so there are lots of other methods as well. Many people use different philosophies and approaches, but I'll show you one approach which is reasonably good and popular in some settings. Okay, people use prior information. So alpha and beta is prior, right? It's a prior information. So it has to come from some scientific study or data or model or some expert analysis and knowledge and things like that. So how do you pick alpha beta? It's a very interesting question. So we'll see some solutions, one solution at least, later on when we solve problems. So notice, if alpha and beta are equal to 1, you get the uniform distribution. So a special case of the beta distribution is uniform. If alpha becomes 1, beta becomes 1, you just get 1, right? So the PDF is flat. Okay, uniform is a special case of the beta distribution. You get flat prior, and estimator is same as what we saw before. If alpha and beta are equal to 0, okay, then you have an estimate that coincides with maximum likelihood. Okay, it's an interesting observation. Alpha and beta are equal, you have a symmetric prior, right? Symmetric about p equals half. Okay, so that's maybe an interesting property. You may have some symmetry in the problem, and that's always picking alpha equal to beta is very, very popular, because I think some symmetry. If you expect a symmetry, alpha equal to beta is popular, but sometimes symmetry may not happen, right? This p might be, incidence of some rare disease, in which case p is very small. So you want a very strongly asymmetric distribution. So then in that case, alpha and beta should not be chosen like this. Okay, so like I said, it depends on the problem, depends on what you expect your p to be with higher probability. So you may depend on n. You can in fact pick also alpha and beta to be depending on n. Okay, so this case is an interesting case. It's slightly advanced. Why you would like to pick alpha and beta to be square root n by 2? Turns out it's an interesting choice as well. Okay, so like I said, it seems interesting to play around with this choice of prior. It could be something interesting in practice. It's quite useful. So we will see how to pick alpha beta in a specific problem case later on, but these are the various possibilities. You pick different types of alpha beta, you get different looking estimators. Okay, so that's all I wanted to say about the uniform distribution, the Bernoulli P samples and the beta prior. Okay, so we're going to move on to another type of example for this Bayesian estimation. We have normal samples now. We've seen normal samples are really popular. They show up all the time. Normal samples with unknown mean and known variance. Okay, variance is known. So this x1 through xn is IID normal with unknown mean, which I'm going to denote as capital M, and sigma square. Why capital M? Again, just to emphasize this is a random variable. It's not a constant. And what am I going to pick as the distribution for that random variable? I will pick a normal distribution. Normal with mean mu naught and variance sigma naught squared. Okay. Notice what's happening here. There is a mean that I'm picking randomly as Gaussian, mean about mu naught. Okay, mu naught and sigma square, those are the normal distribution. Once I pick that, I go and pick samples according to the normal distribution with that mean and actual variance sigma square that's given to me. Okay. So we know the density here. The density is just 1 by root 2 pi sigma naught, whatever. That's the prior density. So this is the prior density. Okay, so prior density is known. What will happen to the posterior distribution? Okay, so let's say samples are x1 through xn. We have the sample mean, right? So this is something that we know. The posterior is m given x1 equals xn. Remember now this is continuous, everything is continuous now, right? Everything is a density, right? This is normal distribution, so x1 is continuous. So all these guys are also continuous. So this is also continuous, right? They are not discrete anymore. So there's no discrete continuous mix here. It's everything is continuous, so everything is density. Okay, so posterior density is proportional to prior density, and this is likelihood density. Everything is density. Okay, given capital M equals mu, what is the likelihood of x1 equals xn, etc. Okay, so this posterior density you can actually substitute in here. So if you look at f of x1 equals x1, xn equals xn, given m equals mu, this will just be e power, of course, I'll say proportional to, because you'll have this 1 by root 2 pi, all that coming in. I'm not writing that down. Minus x1 minus mu whole squared by 2 sigma squared times e power minus. See, remember all these guys are independent, right? Independent. So you can just write it as f of x1 equals x1 given m equals mu times f of x2 equals x2 given m equals mu, so on, right? Product. So that's what I'm expanding here, 2 sigma squared, so on till e power minus xn minus mu whole squared by 2 sigma squared. Okay, so this is what the likelihood will work out to. Prior is just e power minus mu naught by 2 sigma naught squared. Okay, so you can add all these things. This, if you multiply, is the same as adding on the exponent. So that's what I've written here. Okay, so the posterior density has this form. It's e power minus some all these things, e power minus some all these things. Remember, it's a posterior density of m equals mu, right? So that's important to understand. So it's basically m given the s, right? The samples. Keep that in mind. So probable the density of m taking the value mu given s, given all these samples. Okay, so this if you call as s, given the samples, what's the density or density at mu given the samples, yes. So that's what it is. So mu is like this unknown, the value taken by the random variable, everything else is a constant, right? So mu naught, sigma naught, the small xn to xn are constants. Okay, a variable is mu. Okay, keep that in mind. So the posterior density, it may not be obvious to you, it's actually a normal density. Okay, so I'll leave it as an exercise. Okay, it's an exercise to show this. Show that posterior is normal. So what does that mean, normal? It has some form. This guy you can manipulate and make it proportional to e power minus mu minus some mu bar squared, mu bar whole squared divided by 2 sigma bar squared. So it turns out you can manipulate this equation, rewrite it, complete squares, etc., whatever it is that you need to do, and make it e power minus mu bar squared by 2 sigma bar squared. So mu bar and sigma bar are two different things, and this is the posterior mean mu bar. This mu bar, it turns out, is this. Okay. So I'm not going to do it and show it for you. You can look it up, there may be answers given elsewhere, but it's also not very hard to do. It's just writing out that quadratic expression, normalizing it, throwing away all the constants, keeping only the mu in, you will get this form. It's a little bit complicated, particularly sigma bar is also a little bit more complicated than I would like, but this is the final expression that you get. Okay, look at how this expression is worked out. There is the sample mean here, this is the posterior mean, but it is a sample mean plus some prior mean, right? So this is the prior mean and the sample mean. So the posterior mean is a linear combination of the sample mean and the prior mean. Okay, so prior plays a role, sample plays a role, you multiply them by some constants, add it, you get the posterior mean. Okay, so it's very nice. That's number one. Number two, you observe that in this problem, the normal distribution is a conjugate prior. Okay, so this is a conjugate prior. Why is that? Because the class of the posterior density is the same as the class of the prior density. You got normal as prior, posterior is also normal. Okay, so that's conjugate, and you got the posterior mean to be this. Okay, so now if you want to replace it to get the estimator for mu, I'm going to make the sample mean as this capital X1, replace it with the random variable, and then you get n sigma squared by n sigma naught squared plus sigma squared plus mu naught sigma squared by n sigma squared, etc. Okay, so what is the ML estimate? Compare with the ML estimate, right? So mu hat ML. This will just work out as x1 plus xn by n, right? So this will be the ML estimate. Okay, but notice how this sigma square and all is playing a role here in the Bayesian estimator, but it's sort of similar to this. Why is it similar to this? Supposing n becomes really large, okay? If n goes really large, so you will notice that this guy tends to 0 as n tends to infinity. This guy tends to 1 as n tends to infinity. Okay. So while it may look very different from the ML estimator, it has all sorts of other terms. If you let n grow, it becomes the ML, it's sort of tends to the ML estimator. Okay. So at least it's sort of meaningful, but you have this additional sigma naught square floating around, mu naught floating around. What do you do with all these things? Where do they come from? How do you pick them? Okay. Maybe we'll see this in an example later on. Okay. So again, prior was this normal mu naught sigma naught square. How do you pick mu naught? How do you pick sigma naught? I'm not going to do that explain it here. I'll do it in a problem when I pick it up. So we see that the estimate is a combination of data and prior. Okay, very nice combination of data and the prior. The sample mean comes from the data, prior is there. So you can imagine the prior getting updated, etc. Sort of philosophical meaning. If n is very large, then the Bayesian estimate tends to the sample mean. Data ends up dominating, prior is does not play a small role. But if n is small, okay, if n is small, then the prior plays a role. Okay, so that's something to keep in mind. Okay. Also, if you pick the variance of the prior as very large, what does it mean? If you pick the variance as very large, the Gaussian bill is going to sort of become flat, right? So my prior becomes uninformative. Okay, so my prior becomes uninformative. You can check if your sigma naught square is really large also. Again, both these things will happen. They will tend to 0 as n tends to infinity, or sigma naught tends to infinity. So even if you tend sigma naught to infinity, the prior literally doesn't matter. Okay, so it will just converge to the sample mean in that case. So prior becomes uninformative in that case. Okay. So we saw two different sampling problems, quite non-trivial, the Bernoulli P sampling problem and the Gauss normal sampling problem. In both cases, we had conjugate priors, right? The beta distribution was the conjugate prior in the Bernoulli case. The normal distribution is the conjugate prior in the normal case. Remember, we saw a special case of normal where mean alone was the unknown, variance is known. Okay, if there are various combinations possible there, it becomes a little bit more confusing. We are just seeing the simple case. In both cases, we had conjugate priors. In both cases, we saw some very nice properties. The actual estimate is a combination of the prior and the data. Okay, the sample mean sort of plays a role, and it's modified by the prior. Okay, in the beta case, in the Bernoulli case, we had this plus alpha and plus beta in the numerator and denominator. In the normal case, we are multiplying with some factors and doing a linear combination. So, some modification is there, but in both cases, when the prior tends to be uninformative or when the number of samples become very large, the prior sort of disappears. You seem to be getting the ML sort of estimate. Okay, so Bayesian estimates seem to be good from this point of view. Okay, so that's the conclusion of this lecture. In the next lecture, we will see a few problems, and particularly with this this kind of estimation, and how do you pick the parameters of the prior? What are some rules that one can use? We'll see that in the next lecture. Thank you very much.